Welcome to UNSW's Engineering the Future podcast. Today, we are talking about the weird and wonderful world of quantum. We'll discover how a quantum bit, or qubit, has the ability to power revolutionary computing, ultra-secure communication, and precise sensors.
There are certain quantum sensors that can measure acceleration and so on with extreme accuracy that they're now being applied to this way of navigating that potentially one day, not too far from now, you could imagine having navigation systems that actually don't rely on GPS.
That's Jared Pla, an associate professor at UNSW, who is developing new technologies to aid with the scaling of quantum computers. On Engineering the Future, we speak to academics and industry leaders who are embracing cutting-edge ideas and pushing the boundaries of what is truly possible. Join us as we discover how world-changing action starts with fearless thinking on Engineering the Future of Quantum Technologies. Hello, and welcome to Engineering the Future of Quantum Technologies. My name is Neil Martin, and I'm a journalist and STEM communicator working in the Faculty of Engineering at UNSW. Joining me today to discuss the exciting developments in the world of quantum is UNSW Associate Professor Jared Pla. Jared is an electrical engineer and experimental physicist working in the fields of quantum information processing and more broadly quantum technologies. He is focused on developing new quantum technologies to aid with the scaling of quantum computers and to advance capabilities in spectroscopy and sensing. Hello, Jared.
Hi, Neil. Thanks for having me here.
It's a pleasure. Also with us is Professor Peter Turner, the CEO of the Sydney Quantum Academy. Peter holds an honorary professorship in the Department of Physics and Astronomy at Macquarie University, and he's also a member of their Research Centre for Quantum Engineering. He has been involved in quantum information for nearly 20 years, establishing arguably the world's first program aimed directly at preparing graduates for the then emerging quantum technology industry while at the University of Bristol. Hi, Peter.
Hi, glad to be here.
So this episode is very pertinent since 2025 has been officially proclaimed by the United Nations as the International Year of Quantum Science and Technology. This recognises the 100-year anniversary of modern quantum mechanics, which is the fundamental physical theory describing the behaviour of matter and energy at very small scales. Future quantum technologies are slated to revolutionise secure communications, precision sensing, medical imaging, and materials discovery, while quantum computing offers the promise of performing complex calculations mind-blowingly faster than classical computers. Jared, to start off for our non-expert listeners, of which there may be many, would you be able to give a very simple definition of what we mean by quantum?
In my mind, quantum is really any system or object that obeys the laws of quantum mechanics. If you say that to a quantum engineer or a physicist, they might laugh because really deep down everything behaves according to these laws. But typically when we discuss quantum in the terms of technologies, we're talking about technologies that somehow utilize these quantum mechanical laws to do something interesting.
And would that apply to all of those different quantum technologies I've mentioned? Is there a one-size-fits-all?
Yeah, so quantum technologies is a really broad term. I mean, there's many technologies that you use today that have had quantum technologies in them for, decades. And so we usually sort of classify them into technologies that came from two eras. There's something called the first quantum revolution, which happened in the early sort of 1900s. And that gave technologies like transistors, diodes, lasers, which really created modern society as we know it today. So you wouldn't have computers, medical lasers, these sorts of things without these technologies. And these are generally technologies, so transistors, lasers, which you need to understand the laws of quantum mechanics in order to design them and know how they work. But they don't really use quantum mechanics in a particularly sophisticated way to do what they do. And that brings us to the second class, which is technologies which are coming from the second quantum revolution, which is actually currently underway. And these are technologies that use some sort of quantum phenomenon. Now, I'll say some words which we might dig into a bit deeper later on. Quantization, superposition, entanglement. These are all, I would say, quantum phenomenon that you could utilize in some sort of sophisticated way to do things that we couldn't do in the past. And that gives us technologies like quantum computers, quantum enhanced sensors, quantum timing applications, so on.
Peter, in your work with regards to, I guess, kind of knowledge sharing and teaching people about quantum, do you find yourself giving this explanation and going to that kind of basic level quite a lot?
I was thinking about this, maybe 2 steps to understanding quantum in general, or not understanding, of attempting to do this condensed short version. One thing you need to appreciate is that at the lowest scales, the universe is non-deterministic. You need probabilities and statistics to decide what's going on. In other words, I can know everything that there is to know about a certain system, in this case, a microscopic system. And yet I still, for certain measurements, will not be able to say with 100% what's going to happen. There's still probabilities. It's baked in fundamentally. That's no problem. I mean, we deal with statistics and probabilities all the time, if you've watched the stock market over the last 10 days or so. So there's nothing really earth-shatteringly weird about that. What is really weird is that at the fundamental level, quantum mechanics makes use of not probabilities, what we call them amplitudes. So they're like probabilities. You can get probabilities from them, but they can be, for example, negative, which is, your head explodes if you try to understand that in a classical and a non-quantum way. And so, for example, 2 processes, one of them can have a positive amplitude and one of them can have a negative amplitude. And unlike any classical statistical process, those 2 things can cancel and give a 0% chance of something happening. That just doesn't happen classically. And so, as Jared said, this second generation of quantum technologies are trying to actually harness those kinds of effects and see what we can do with them that are new. And it changes information theory, it changes computation, it changes communication. And we're still figuring out what that means.
I think you've both done a pretty good job of explaining it there, but I think maybe on some level people just have to trust that this is happening. When you go down to those scales, some really weird things happen and they're not really going to be able to understand them. But I think we're going to talk about quite a few different quantum technologies, but probably the one that most people will have heard of in the general media is quantum computers, which I understand are a very specific thing in the quantum world. But would it be correct in saying that quantum computing is what a lot of this stuff is actually then fundamentally based on, or is that incorrect?
I think it's fair to say that it's the kind of holy grail of the field in some sense. A completely error-corrected utility scale quantum computer is kind of the main goal. We kind of split quantum technologies into these 3 rough categories, right? So I think you mentioned sensing, communications, and computation. So computation is the top end, if you like, is the most complex of those things.
Yeah, and it draws certainly the most attention, the most funding, but in a sense for a reason, because the potential of quantum computing is extreme.
And again, if we take it back to basics, it works on a mind-blowingly fast scale. Is there an easy way to describe kind of how?
Again, never an easy way, I don't think, to capture these things. I talked about this interference earlier, and you can maybe start to grasp some of the ideas behind quantum computation there, because you have these processes that can interfere in this totally non-classical way to positive probabilities becoming 0 or whatever, to canceling each other out. Then you start to think, okay, can I harness that? Is there something I can do? In other words, could I do a kind of calculation, if you like? This is a new type of thing, a probabilistic calculation, where even without knowing what the answer is, can I just engineer this situation? Can I program this machine so that even though I don't know the answer, I know that whatever the wrong answer is, it's going to cancel out. And therefore, by definition, the probability of the right answer must go up at the end of the day in the output of this thing. So that gives you an idea of what's going behind designing these quantum algorithms and stuff in these computations.
So you may have heard of a bit, a byte, a megabyte. A bit is an information carrier in a conventional computer. You think of it as a light switch. It's a 0 or 1. It's on or off. A quantum bit is also 0 or 1. It just has the additional property that it can be in this thing called a superposition of 0 and 1 at the same time. And any combination, right? It could be 20% 0, 80% 1. Now, if you have 2 quantum bits, then you have the possibility of both of these things being 0, both of these things being 1, 1 being 0, 1 being 1, or vice versa. But you can also have any combination of all these different combinations, okay? Whereas in a classical computer, your 2 bits can only ever be at any one time 0, 0, or 0, 1, or 1, 0, or 1, 1. And so how it's often explained is in a quantum computer, because you can have this state where you have your quantum bits, your 2 quantum bits being 0, 0, plus 0, 1, plus 1, 0, plus 1, 1, all combinations at the same time, you just run it through your algorithm and it does calculations on every single possible combination of bits. And so you get all the answers that you could possibly expect at the output. That's not how it works. Because as Peter mentioned earlier, quantum mechanics is a probabilistic thing. So when you actually go to measure the output of your system, it probabilistically collapses into one of the possible answers. And so you only get one answer out. And so as Peter described, you need to be very clever with the way you design your algorithm so that the right answer reinforces itself at the end of the computation and the wrong answers cancel themselves out.
But fundamentally, it's doing things much, much faster. And I guess the follow-on from that, if we just take that as an assumption that that's true, every single calculation that every single computer is doing is faster?
Okay, no. Short answer to that is no. So there are examples of certain types of problems that have a structure that is amenable to this kind of interference cancellation effect. The famous one being Shor's algorithm around factoring large numbers. But we also know that there are problems where a quantum computer will just not be able to speed that up. It doesn't have a structure. As far as we know, the problem doesn't have a structure that lends itself to this kind of interference type of procedure or phenomenon. So I think that's one of the key things to make clear is that quantum computing, and by extension, quantum information theory, it's different, it's not faster. And for certain problems, that difference can make a huge, incredible speed up. So the art here is figuring out which problems have structures that we can take advantage of, which ones don't. And I guess the one place where most experts are very, very comfortable is saying, yes, I think we are going to see huge improvements in speed or other resources in terms of computing and by extension comms and others, are simulating quantum systems or trying to answer questions about quantum systems that even supercomputers can't answer right now. And it's surprising how small a molecule is or a material cell can be, and a supercomputer still can't answer the kinds of questions that hopefully a quantum computer can. So we're quite confident that quantum computers are going to be able to, new materials, pharmaceuticals, chemistry, anything that's quantum, these machines that we're hopefully going to be able to engineer will just, for fairly obvious reasons, be able to simulate them very, very quickly, much more quickly than a supercomputer can. But then when it comes to other applications, optimizing, you hear about portfolio optimization or machine learning, big data problems. The confidence level, certainly speaking for myself, I think a lot of the community, confidence level starts to go down. These are all research questions that we're trying to figure out. Whether we're going to be able to see really impressive improvements in speed or other resources in quantum computers on those kinds of applications down the road. Still open research questions that we're reaching out to the people who do those kinds of things using supercompute in a bank or a pharmaceutical company or a materials company, whatever now, trying to get more of those people involved. So your engineering audience, that's an invitation. Definitely come and speak. Don't leave this to the physicists, to the quantum physicists. We need experts from these other fields to come in and help answer those questions.
We can use this as some kind of advert to get people's interest.
Certainly, yeah.
I think that's a very good point Peter made. Whilst quantum computing definitely now has somewhat transitioned to industry, there is still big questions to be solved and fundamental research that needs to be done and supported.
Still some huge breakthroughs that we need to find.
Absolutely.
And my understanding is that quantum computing, although it's maybe the killer application, might be the one that actually ends up getting developed further away. A lot of these other quantum technologies that we'll come on to talk about might come online quicker. Is that correct?
If you give me a qubit, this is what we use, a quantum bit, whatever this thing is, it's going to be superconducting or photonics or silicon or whatever, dots. Whatever this quantum, let's call it this, not magical, this very special, strange this device is, a qubit, could be very small, but in reality, it's probably going to have a bunch of other stuff around it. If you give me one of these things, maybe it's a quantum sensor. Because of the way quantum mechanics work, and if I engineer it right, it can be extremely sensitive to magnetic fields, for example, whatever. This kind of, maybe that's good for medical imaging, whatever. But that's the quantum sensing thing. If you give me two of these things and they talk to each other quantum mechanically, now I have a communication system. That's, again, grossly oversimplified, but logically it kind of stands. But then for a computer, I need thousands and thousands and thousands and thousands of these things talking to each other in this coherent quantum way in order to get these interferences to work out in my algorithm. So hopefully that gives you an idea of why these three categories of quantum technologies, as you said correctly, I think the full quantum computer one is probably farther down the road because it's the most complex.
On the sort of quantum sensors side, like an example of that is a squid. So it's something called a magnetometer, a device that senses magnetic fields. And SQUID is not the creature in the ocean. It's a superconducting quantum interference device. It's basically a loop of superconducting metal. And a good success story here is that actually in the 90s, the CSIRO, so our national science research body, worked out how to make these SQUID, these magnetic field sensors, using superconductors that superconduct at higher temperatures than normal. So these are called high temperature superconductors. And what that allowed them to do is to actually put these things in planes and fly them across Australia and other places and detect iron ore and other mineral deposits underground, something you couldn't do before. And this has been estimated to have generated billions of dollars in mineral exploration over the past 10 years. So these are things that have existed for some time. They're here, they're delivering benefit.
And if we stick on sensing, Peter, like you said, that's possibly the most basic one or the least complicated
again,
one.
At the risk of making people who work on this angry, it's not to say it's simple, but it's conceptually simpler than a computer.
I understand, and I think it's useful for the majority of our listeners, that explanation that you gave. But sticking on sensing, you mentioned a few in passing. Maybe you could give a little bit more detail of those kind of sensing capabilities and what impact you think they will continue to have over the next 10, 15, 20 years.
I was in the UK before coming to Australia, and an example that was brought out early on there was same kind of sensor, but the application was finding infrastructure underneath the ground in cities. So London and other cities in Europe, they have 2,000-year-old Roman infrastructure, lead pipes and stuff like that, where no one knows where they are. And of course, they have to dig them up in very expensive real estate areas of London. It costs a lot of money. It's so expensive to do that actually motivated building these kinds of quantum sensors that would non-invasively go in and find this underground infrastructure is another example of an application. Another one I've heard of, again, is it's clock-related, atomic clock-related, but having these things in satellites, and they're so sensitive that you can do gravimetry. You can measure the Earth's gravitational field so sensitively from orbit that you can identify mineral deposits and things like that, things with different densities underneath the ground, hundreds of kilometers away.
So I have two sensors, one perhaps sensor adjacent to add to that. So often sort of lumped in sensors as atomic clocks. And actually they've been used for decades. So for example, GPS. The reason I was able to almost get myself to the location of this podcast today, I did get a bit lost, was because I was able to put into Google Maps the location, and Google was accurate, and it would have had me here within a meter accuracy, right? And the way that you actually do that is something called trilateration, where you have a number of satellites up in the sky, which are sending signals to you at the speed of light. And by measuring the time it takes for that signal to reach my mobile phone and doing that with a number of satellites, I can triangulate my position. It turns out that in order to do that, you need to have the satellite and your phone, your GPS receiver, sort of synchronized with a very, very high accuracy, right? So you need these timers, which are extremely accurate. And actually, the only way really to get good accuracy is to use this thing called an atomic clock, which is basically a clock which is synchronized to some internal energy levels inside very stable atoms. And they've existed for some time, and they're used in GPS.
So I guess the follow-on question I have with that, and I've worked with academics, I think, in that field, my question was always, what's then the implication? If you can be more precise about where you are with regards to GPS, what's the benefit of that? Most people might say, well, I'm within a meter of the place I'm going to, if I'm half a meter closer, or what's the benefit of being super precise in that?
There are some ideas what you can do with devices that are even more accurate. And Peter mentioned one, for example. You can look at time dilation due to gravity and other effects, and that allows you to probe things under the ground that you couldn't see, from space. Like, these are the crazy sci-fi things that you could potentially do if you have these timing devices with that level of accuracy.
I would just add, kind of as an invitation to the younger people listening. I mean, again, like any technology, this will have unforeseen benefits and risks that will have to be managed. But it's the younger generation that's going to discover these things once they have them in their hands, right? Like, we have a few ideas, but like any other technology, it's once you start playing with it, once you start using it, that the ideas really start to come.
One other potential sensing application I think is interesting, it's along those lines, is something called inertial navigation. And so there are certain quantum sensors that can measure acceleration and so on with extreme accuracy that they're now being applied to this way of navigating, that potentially one day, not too far from now, you could imagine having navigation systems that actually don't rely on GPS. That's actually really interesting from a defense perspective as well. The first thing that goes down in a conflict is the satellites or other satellites. That's either through jamming or other means. And so being able to navigate your defense cruiser or aircraft without the use of GPS is extremely interesting for them.
You'd mentioned quantum communications and cryptography as kind of maybe the next level, and I know that's a very basic way of putting it, the next level up from sensing. Where do you see that whole field developing? Where are we at the moment?
One idea to make sure when you talk about quantum communications is that there are two aspects to this, and certainly one of them's become just very recently much more, it's become more important to separate these two. So there's the quantum computers as a threat to what we'll call classical cryptography, the stuff that we use on our phones and the internet all the time. And then there's quantum cryptography, so replacing classical cryptography with new quantum infrastructure and quantum cryptography. So classical cryptography, as I understand it, is based on something called information theoretic security. They're based on problems that we believe are so hard to solve, and we believe it so much that we're willing to do our banking over the internet. So factoring large numbers being the key one. And this is exactly what Shor's algorithm shows. An eventual quantum computer that's sufficiently powerful would be able to factor large numbers and therefore crack that crypto system. There's something called post-quantum cryptography now, or quantum resilient cryptography. I think there's a few words for it, which is classical cryptography that isn't based on factoring large numbers and therefore based on things like lattice theory and stuff that we believe right now is going to be resistant to even a powerful quantum computer down the road. And that's being rolled out now. So NIST, the standards organization in the United States, has just very recently released some candidates for post-quantum cryptography. And a lot of organizations around the world are starting to roll this out. So that's one of the first places that a lot of your listeners probably, at least in their organizations, might come across cryptography. But it's not quantum cryptography, it's post-quantum. It's classical cryptography that's resistant to a quantum computer.
Yeah, so you might ask, why are you rolling these, post-quantum cryptography algorithms out now? We don't have a quantum computer. We're not post-quantum. But an important point is that we are susceptible to future quantum attacks now. So any data that you send that is based on RSA encryption, so be it of a military or a financial nature, there are people that are mining this data in the hopes that, in 10 years' time or potentially sooner, we have a quantum computer and they can break the encryption on those messages. And so it's important for, very sensitive information to be encrypted now with these algorithms that we think won't be susceptible to attacks from quantum computers in the future.
And I guess all of this stuff is just happening in the background. The general public, they don't necessarily need to know the details, or they wouldn't understand the details, but they just have to trust that the people who are the experts are doing this to help them.
That one might just be rolled out as an update on your phone and you won't even realize it because it is classical cryptography. The other category was actual quantum cryptography, so more particularly quantum key distribution. So this is actually sending quantum information between two parties to establish a secret key and then go and do your cryptography that way. This is, as far as we know, the laws of physics, this is kind of physically guaranteed security. Unless quantum mechanics is wrong, which we have no evidence is the case for over 100 years, anyone trying to crack this key will be detected. So that's really kind of new quantum technology. And there are efforts around the world. You hear about fiber optic connections between cities that are running these kinds of quantum key distribution protocols now on a small scale, relatively small scale, in order to test them out.
And if I bring it back to the benefits for the general population, improved security sounds like it's definitely one of them. Is there a speed issue there as well with communications? Does it make communications quicker? Does it make connections more stable?
I think on the classical post-quantum cryptography, I'm not sure there'll be a huge difference. On the quantum key distribution, certainly there is a bandwidth issue. It's not going to be faster. If anything, it's going to be quite a lot slower. I don't think it's going to be, at least with our understanding of things now, going to be something that's general use. It's for certain applications like financial institutions, military.
Certainly for the more hardcore information theory people, there is things like communication complexity in the same way that there's computational complexity. In other words, what are the resources I need in order to communicate, that two parties need in order to communicate? There's a lot of research that's been done in the quantum versions of those things. So there is quantum communications complexity research being done. The number of times that two parties need to communicate to each other might be reduced, and again, on certain problems. So it's not a blanket. Quantum does not make communications faster in the same way that quantum computers don't make computation faster. It's just that if we can find certain types of communication problems that quantum is amenable to, that's the research.
And when we look at those quantum technologies in a general sense, what are the big engineering challenges that need to be overcome that people are working on now to bring them to fruition?
The other quantum technologies, quite a few of them are already here. They need to be made better, more reliable, more stable, so on. But that's sort of on the years time scale rather than decades. With quantum computing, look, we have had some recent quite big breakthroughs in the space. There's almost one, every month now. At the end of last year, Google actually published a paper on their new chip, which they call Willow, which was able to demonstrate a really important problem, or I'd say roadblock in quantum computing, something called quantum error correction. So in order to build a quantum computer, you need to be able to correct errors that may happen on your quantum bits. In a classical computer, this is pretty simple. If I have a bit and I want to protect it against errors, I just copy that bit 10 times, 100 times. And if two of those are 0 and the rest are 1, I know that those two that were 0 somehow flipped and that was the error. And I just reset them. With a quantum computer with quantum bits, you can't do that because there is this fundamental law called the no cloning theorem, which means I can't copy my quantum bits. And so what you end up needing to do actually is to take very large numbers of quantum bits, say 10,000, and encode your quantum information in some entangled state of those 10,000 qubits. And when you do that, you sort of spread your quantum information out amongst 10,000 qubits. It turns out there are some protocols you can use to correct errors that may occur. But the problem with that is you have a massive resource overhead. In order to create one actual quantum bit, we call it a logical qubit, you need 10,000 qubits, physical qubits. And so imagine trying to scale that up, in particular for some systems where you can see these qubits with your naked eye. It's looking a bit daunting.
It sounds like the challenge, though, is that everything's just super complicated. Is that correct?
It's going back to something Jared said earlier on, which was, I think I said something, quantum mechanics is a microscopic phenomenon. And Jared was making the point that there are systems that are less microscopic. I don't know if I can say macroscopic yet. Interpret those words however you like. Observing these effects in bigger systems. In some sense, the problem of quantum technology is coaxing these quantum effects out of big systems, which just doesn't happen naturally. So that is the challenge. There's all these different platforms or technologies that we're trying to do these things in: superconductors, semiconductors, photonics, and it's still not sure yet which one is going to win in order to do this. As Jared said, error correction is absolutely critical. We know that whatever the technologies are, because quantum mechanics is so sensitive, there are going to be errors. This whole field would have died if error correction hadn't theoretically been discovered in the 1990s, also by Peter Shor and others, not long after Shor's algorithm was discovered. So it's absolutely fundamental.
And to pick up something that you said there, Jared, I think there's a joke in the community that quantum computers they're always just 20 years away. Whenever you speak to someone, it's, they're 20 years away now. It never seems to get much closer. A, do you think that's valid? But B, can you see in 20 years' time that you'd be saying, no, there is a computer?
Look, I think I'm guilty of making this statement a few times myself as well. I think the problem is that, even 5 years ago, we just didn't have enough information or evidence to be able to put a more accurate timeline on the development of these quantum computers. You were always hopeful, but there was still some very big unanswered questions. I think with some of the big demonstrations, we have much more confidence that this is possible. However, there's still a lot of work to be done, fundamental work on making better codes for error correction. And then on the other side, there's still a lot of work to be done on improving the actual hardware. So the actual physical qubits themselves, we need to get those intrinsic or inherent error rates down.
I guess a key part of this, Peter, might be training the next generation. How important do you think education is, but maybe also information for the general public, but more so education of bringing these people through that are going to understand these things and develop them?
Yeah, it's critical. You cannot go to an international quantum technology meeting, and I've been to quite a few in the last few years, and they're not just the academic ones. There's much more industry and government involvement as this industry starts to grow. You can't go to one of these meetings and have people not within the first few minutes mention workforce and talent and skills as a big concern. It's everywhere. The number of people who understand, it's quite a small community over the last 25, 30 years, obviously growing. But what Jared has said is giving you an idea of, this technology has to scale quite significantly in order to reach this utility. The number of people kind of needs to scale as well. So it's been experts, and it still is experts. When I say expert, maybe I mean PhD level, research level trained people. We still need those desperately. Like I say, there are breakthroughs that still need to happen in order to realize these technologies. But of course, there's also, as an industry grows, there's all the skills other than the real deep technical expertise. There's classical software engineers and product designers, and then just the business end of things and whatnot. So CSIRO here in Australia has estimated 20,000 jobs by 2040. And I think Kathy Foley, our previous chief scientist who was instrumental in that roadmap that CSIRO did, has certainly said to me and others that that's a pretty conservative estimate on the number of people that are going to need quantum skills at some level. And then you pile on the rest of STEM, science, technology, engineering, mathematics. There seems to be frighteningly less interest nowadays from young people in those kinds of things, which I find hard to believe given all the cool stuff that's going on. We need certainly to raise people's interest.
Jared, you obviously work at UNSW. You see some of this new generation coming through. What more do you think needs to be done to increase that cohort?
Yeah, look, we're trying to tackle this problem at UNSW very actively. We've actually created the world's first undergraduate quantum engineering degree that's actually been running for a few years. And we have healthy enrollments in that degree. One thing Peter mentioned was this CSIRO report on Australia's quantum technology industry. And actually, some of the numbers are really, really great for us, but also quite scary. So even in 10 years' time, 2035, they predict the quantum technology industry, so that's quantum sensing, communications and computing, will be generating about $3.3 billion for the Australian economy, and we'll need an extra 3,300 trained quantum engineers and technologists. This is a workforce we don't currently have. And you can't solve that issue in 10 years' time. You have to be working to solve that now so that we have that trained domestic workforce in 2035.
And does that go back to putting out information to get people interested, to get young people knowledgeable about the industry and what they might be working on? And maybe this podcast could help that.
Yeah. Yes. Thank you. Absolutely. So career awareness, and it's not just the students, it's their parents and teachers and whatnot, and just making it clear that this industry is coming. I think AI has really obviously exploded onto people's consciousness in the last few years. And it's another example of research field that goes back decades and decades and decades. In some sense, you knew this was coming and people seem to wait until the last, and then everyone's playing catch up. Quantum, especially in Australia, quantum has been around for decades and Australia doesn't have to catch up. The skills are here. We just need to scale. So yeah, it's an appeal to do more of that. I guess I should say a bit about Sydney Quantum Academy. Our organization is doing this where Macquarie University, University of New South Wales, Sydney, where Jared is, University of Sydney, and the University of Technology Sydney, 4 universities in Sydney that have had quantum research groups doing amazing research for decades, kind of individually. The New South Wales state government came together about 5 years ago with those 4 universities and said, let's create the Sydney Quantum Academy, SQA, with a real focus on building that talent pool and taking the amazing expertise that is in Sydney and by extension Australia to the next level. So SQA does that. We do PhD scholarships, we do undergraduate summer placements, and we're doing more and more outreach at the high school level for students and teachers in order to try to address this problem. So there's a bunch of ways to come and work with us in doing that.
Do you feel that maybe high school students might just look at quantum and think, it's just too complicated? I just can't get my head around it.
So, but how can you look at AI and not say the same thing? Or how can you just look at how a computer works in general and not say the same thing? I don't feel like quantum's bringing anything new to that. I feel like the message is the world is definitely complicated, getting more complicated. I think a key message to get across as well is that quantum technology is manifestly interdisciplinary. I think the reaction that you kind of described is a very something I'm trained as a physicist, and it's something that physics departments have been grappling with for decades and decades, right? People saying, oh gosh. Our undergraduate society had a t-shirt saying, what makes you think I care how much you hated physics in high school? It's that kind of mentality. But quantum technology isn't just physics. It's computer science, it's mathematics, it's engineering, it's materials. And then it's on the application side, of course, it touches everything that information technology touches. So it's just hugely interdisciplinary. There's so many ways in, so many different interests that you can have that it's going to touch upon. Yeah, really, really, really exciting.
And I guess my thought of what you've been speaking about in this episode is that you can see that all of these things have real world impact. So people getting involved, young people taking this up and developing things which are going to have real impact on people's lives.
Yeah, absolutely. Like I say, quantum technology touches on everything that information technology touches on. And it's very hard to come up with something that information technology hasn't changed in the last 50 years, right? So it's the potential is hard to overestimate.
I think you've both done a really great job of explaining quantum technologies and the future and the potential. Just as a final question, if you had one wish for where quantum technology will be in, let's say, 20 or 30 years, what would you wish for?
Well, I would hope by 20, 30 years' time that not only do we have a working quantum computer, that we actually have multiple different types of working quantum computers. There are different companies working on their own systems. And just like we have different options for conventional computers, you can buy it from IBM, from Dell, from Lenovo. It would be good to have sort of competition in that space. I think competition is very healthy. And on top of that these computers or these quantum computers are at a size and scale that they're actually solving globally significant problems. Looking at things like creating more efficient catalysts for chemical reactions. This has the potential to, bring us closer to net zero emissions, for example. Designer drugs and vaccines for different diseases and ailments. And, the potential applications, I think, in this quantum simulation space, which is what most of those applications refer to, are pretty life-changing. And I think by that time, we should be seeing some of these applications.
Same question to you, Peter.
Well, yeah, it's hard to answer it better than Jared has. I can give the not controversial, but the scientist answer, which is kind of fun to point out. And it's not, I'm certainly not the first to point this out, but the physicist might answer, well, I hope that in 20 or 30 years, we prove that it's impossible, because then we will have learned something about the universe that we'd simply, quantum mechanics has been so good for so long, it's almost annoying. So,
and many of our colleagues will be unhappy with that answer.
Yeah, a lot of people would be unhappy. I'm not actually advocating for it, but it just shows that when you're a scientist, you get to play both sides of the field. Either you develop this amazing technology with all the amazing applications that Jared just pointed out, or you prove that it's impossible and you've learned something about the universe that's going to open up new research directions. So it's win-win.
Well, it'd be fascinating maybe revisiting this episode in 30 years' time, pulling it out of the archives and seeing where we actually are and what those impacts have been. It's been really interesting to hear your expert thoughts and opinions on this. Professor Jared Pla, many thanks for joining us.
No, thank you again for having me, Neil.
And also Professor Peter Turner, it's been a pleasure to talk to you.
Likewise.
Unfortunately, that's all we've got time for. Thank you for listening. I've been Neil Martin, and I hope you'll join me again soon for the next episode in our Engineering the Future series. You've been listening to UNSW's Engineering the Future podcast. Don't forget to subscribe to our series to stay updated on upcoming episodes. Check out our show notes for details on in-person events, panel discussions, and more fascinating insights into the future of engineering.